Hello, and welcome back to Physics 41, University Physics 3. So this is now the last video lesson for Chapter 4. So before we proceed, let us review what we have discussed so far in this chapter. So we have discussed about the capacitance, charge, and energy, which revolves around this equation here. Capacitance is Q over charge per unit voltage. So in general, if you have a parallel plate capacitor with a dielectric and dielectric constant K, then the capacitance only depends on the dielectric constant, the area of the plates, and the distance between the plates. And the energy stored in a capacitor is just 1/2 CV squared or Q squared over 2C or 1/2 Q times V. So if you have capacitors connected in series, then the capacitance is given by equivalent capacitance of those capacitors connected in series is given by this equation, wherein the equivalent capacitance will become smaller. However, if you have capacitors connected in parallel, you just add up all of the individual capacitances to get the equivalent capacitance, which is now larger than the individual capacitances. So for this last video lesson, we will just have more examples on capacitance and dielectrics. So let's now have an example. So let's have a capacitor network as our first example. So for the given capacitor network, where C1 is 2 microfarads, C2 is 0.5 microfarad, C3 is 1 microfarad, C4 is 1 microfarad, and C5 is 2 microfarads, find the capacitance of this network between points and B. So essentially, we want to convert this into just a single equivalent capacitor between points A and B. That's what we will do. Okay. So similar with what we did last time, before we can proceed with that final form, we need to identify first the basic series and parallel connections. So from this figure, we see that C3 and C4 has a series connection. What is the connection between C1 and C2? It's neither parallel nor series. For C5 and C4, again, this is not a series connection because there's a junction here. This term, this node here, is what we call a junction. And a junction is not a property of a series connection. A junction is a junction is a property of a property of a parallel connection. Parallel connections have junction, but series connections don't have junction. So C4 and C5 doesn't have a series connection. Okay, so the only obvious basic connection here is C3 and C4, which means I can actually convert this system into something like or network. It's something like this. This is my C1, this is my C5, and this is C2, and I can combine C3 and C4 into C3 4. Okay, so after that one, it will now be obvious. It's obvious that C3, 4, and C2 have a parallel connection because both of their upper plates are connected, both of their lower plates are connected. Take note, these lines here, these black lines here, are just conductors, basically your copper wires. So parallel connection here. So by the way, let's solve for C3, 4 first. So this is a series connection, so the formula will be 1 over C3 plus 1 over C4 to the power of -1. So you will get so C34 will be 1 over C3 plus 1 over C4 to the power of -1. And that will give you, so C3 is 1 microfarad, C4 is also 1 microfarad. So you have 1 over 1 plus 1 over 1, 1 plus 1, so 2. So we'll get inverse of 2 is 0.5 or 1 half. So you will get 0.5 microfarad. So this is 0.5 microfarad. And then it's in parallel with C2. So C2 is 0.5 microfarad also. So 0.5 microfarad plus 0.5 microfarad. Therefore, I can reduce this into just one single capacitor called C234, which is equal to 1 microfarad. And then these three C1, C2, 3, 4, and C5 are now in series. So I can now finally solve my equivalent capacitance as 1 over C1 plus 1 over C234 plus 1 over C5 inverse. So you use those 1 to get C equivalence of 0.5 microfarad. Again, by the way, when you solve a capacitor network like this, I will require you to draw your solutions first. So draw the simplifications step by step, just like with what we did in the previous example. So here you draw from this, you need to draw the circuit again on your paper, and then simplify your drawing until such time that you will get only one capacitor, one equivalent capacitor. So you must do that in your actual solutions. So I'm doing that, but I'm just erasing it because I only have a very small space to work with. Okay, so that's it for this example. So it's, if you have a capacitor network problem, it's actually just quite easy to solve. So you just need to simplify. Okay, so how about now a combination of a capacitor with an electric problem with a capacitor network problem? Okay, so you have a network of capacitors here. You actually have 12 capacitors, where 4 of those are in this one, in just one capacitor here. So find the expression for the capacitance of the capacitor with the dielectric in this one. So if the given values of the area of this plate here, and the distance d of the plates here is given by this one, and K1 is 1, K2 is 2, K3 is 3, and K4 is 4. So the dielectric constants are given. So what is the equivalent capacitance of this whole network? So this network on the right here is actually quite pretty easy to solve. So C6 and C7 have a series. You can combine this one, and then C5, C6, 7, and C8 are in parallel. You can combine that one, and similarly for the capacitors below here. So the problem actually lies with this one here. How do you solve the capacitance of that capacitor? So I'm just gonna draw that capacitor again. Okay. Okay. So how do you decode this capacitor? So I'm just gonna go to my sorry, notes view. is my notes here. So this is our capacitor. So how do we decode this? So you will notice that this actually looks like a series connection of two capacitors, where the first capacitor has two dielectric constants in between them, K1, K2, and the second capacitor also has two dielectrics between them, K3 and K4. So do you agree? So the lower plate of this, if assuming this is positive, the positive plate, this is the negative plate, this is the positive plate, this is the negative plate. So if this is the negative plate and this is the positive plate, so since these two plates are, if this is a negative plate and this is a positive plate, since these two plates are connected, then therefore it will just be neutral. So similar to this region here. Now, furthermore, this this network, this capacitor is actually just two capacitors in series. Sorry, in parallel rather, because the head of K1 or the head of C1 is connected to the head of C2. Same goes for the lower plates. The lower plates of K1 and K2 are also connected. It's a parallel connection. So similarly for the capacitors below, it's also like that. It's K1, K2, K3, K4. So this is actually the equivalent network of this capacitor here. K1 and K2 are connected in parallel, K3 and K4 are connected in parallel, and both these connections are connected in series. Okay, so for the first question, what is now the expression for the capacitance of this network? So you will notice that all of the capacitors have a plate area of A over 2, since this whole area here is A and this whole separation distance is D. So their plate area is A over 2 and their separation distance between the plates is D over 2. Therefore, without the dielectrics, they will have the same original capacitance in vacuum. So their capacitance in vacuum will actually be like this. So C naught will be equal to epsilon naught. You have A over 2 over D over 2. So the 1/2 will cancel each other out. So A over D. So if you use the given values, you will actually get, substitute the given values, and you will actually get 0.24 farads. 0.24 farads. So therefore, C1 is just equal to K1 times C naught, this value. C2 will be K2 times this value. C3 will be K3 times this value, C naught. And C4 will be K4 times this value here. Okay, now if you go back to this figure here and try to find the equivalent capacitance, so you will notice that these are just in parallel, so meaning C1 plus C2. So C12 will just be equivalent to C1 plus C2, so that will be K1 plus K2, and I just factor out their common value, C naught. And C34 will be the same, K3 plus K4 C naught. So this is C34, this is C1 2 here. Now this is in series, so therefore C1 2 3 4 is just 1 over C12, which is this one, K1 plus K2 C naught, and then 1 over C34, which is K3 plus K4 C naught. So to the power of negative 1. I factor out 1 over C naught to the negative 1, and that will give me C naught. So you have C naught, which is just 0.24. And 1 over K1 is 1, K2 is 2, so that's 1/3. K3 is 3, K4 is 4, so that is 3 plus 4 is 7 to the power of negative 1. And this is actually just 2.1. So 2.1 times 0.24, so farads. So you will get C1234 as approximately 0.5 farads. So that is C1234. So I hope you can see my solution. Okay. But that's a generic flow. So this is the equivalent network of this capacitor here. Okay, and you will get an answer of 0.5 microfarad. So actually, for this problem, that is the only crucial thing. This here is pretty much elementary. So C67, for instance, the combination of C6 and C7, 2 farad and 2 farad in series is 1 farad. So 1 over 2 plus 1 over 2, we get 1. Similarly, for C10 and C11, both are 2 farad, so meaning they're also 1 farad. Their series connection is 1 farad. So you have C5, then C6, 7, and then C8 all in parallel. So just add the 3, and you will get from 5 to 8, 5, 6, 7, 8, you have 4 farad. Similarly, for 9 to 12, you get 1 farad, and this branch here is also 1 farad, and plus 2 farad, you also get 4 farad. So C5 to 8 here is in series with C9 to 12. So you use the series formula, and you will get 2 farad. So finally, you have this whole branch here is 2 farad, and it's in parallel with the 0.5 farad. So it's in parallel with the 0.5 farad capacitor with the electric. So just add the 2 because it's a parallel connection. So 2 plus 0.5, you will get the final equivalent capacitor of this network is 2.5 microfarads. Okay. So let's have a last example. This is transferring charge and energy between two capacitors. So this is your setup. You have a capacitor C1. You connect it to a voltage source, 120 volts voltage source, such that it stores a charge Q sub 0 or Q naught. Now, you remove the voltage source or the battery. So you remove the battery now, and then you connect your capacitor to another capacitor in order to charge this capacitor here. So the question now is, if the switch is left open, if C1 is not yet connected to C2, what is the charge Q naught and the initial stored energy U1 in the capacitor C1? So of course, when the switch is open, so Q naught is basically the capacitance times the voltage. So the charge in capacitor 1 and the voltage of capacitor 1, which is 120 volts. So you substitute the value. C1 is 8 microfarad. Micro means times 10 to the negative 6. Multiply that by 120 volts, and you will get 960 times 10 to the negative 6 coulombs, or 960 micro coulombs. Okay, and what's the energy? So you can use for the energy, again, you have different choices. You can use CV squared, which is usually the obvious choice. So capacitor of U1 is C1 V naught squared. Or you can also use Q squared over 2C, and you already have solved for Q. But this is the much safer formula since C1 and V naught are given. So you use this formula, substitute all the values to get a value of 0.058 joules. Okay, now you close the switch. Now, when you close the switch, you are actually now charging the second capacitor. The first capacitor is now charging the second capacitor. So the connection is actually a parallel connection. So this is C1. This is now your C2. So some of this 960 microcoulomb charge, since this is a parallel connection, some of this 960 microcoulomb charge will remain in C1, and some will go to C2, will be shared to C2. Until such time, the sharing stops when the voltage of C1 equals the voltage of C2, since they are both this is a parallel connection. So the voltage of this one is V1, the voltage of this is V2, and V2 and V1 are equal to each other. Say they're equal to some constant some value V. So the charge of this C1 is Q1, the charge of C2 is Q2, and if you add the two charges, Q1 plus Q2, you will get the original charge, Q0, 960 microcoulombs. Okay, so the question now for the second problem is, after closing the switch and disconnecting the potential source, what is the potential difference and charge across each capacitor? And what is the total energy of the system after we close the switch? So basically, we need to find V1, V2, which is just the same, Q1 and Q2, and the total energy of the system, which is just the energy of U1, capacitor 1, plus the energy of capacitor 2. Okay. So how do we do this? So I'm just gonna erase everything first so I can have more space in my board. So this is a parallel connection. So meaning Q0 is Q1 plus Q2. But Q1, according to the formula, C is equal to Q over V. So Q is C times V. Q1 is just C1 times V1, which is V. And then Q2 is C2 times V2, which is just V, because the two, V1 and V2, are just the same. And we will let their voltage be V. Okay. So this is equal to Q0. So therefore, I already know Q0, C1 and C2 are given, and but the voltage is unknown. So we can now solve for V. So solving for V from this equation, so we have V is equal to Q0 over C1 plus C2. So substituting all the values, you get V is equal to 80 volts. Therefore, V1 is 80 volts, V2 is 80 volts. And since Q1 is just C1 times V1, where V1 is just equal to V, 80 volts. So substituting the values of C1 and V1, this will give you this value here. Q1 will be 640 microcoulombs, and Q2 will be 320 microcoulombs. You'll notice that if you add these two, you will get 960 microcoulombs. So the charge is divided among the two capacitors connected in parallel. And of course, V1 and V2 is equal to 80 volts. Okay, so that one. So for the total energy, you just solve for U1, which is just, you can solve for U1. U1 will just be 1/2 C1 V1 squared, and U2 will just be 1 half C2 V2 squared. And you add those two, and you will get a final answer of 0.038 joules. Okay. So, if you will notice, before you connect the first capacitor to the second capacitor, the energy of the first capacitor is 0.058 joules. But when you connect it to the second capacitor, the total energy of the system is now only 0.38 joules. So what happened to the 0.02 joules? So some energy is lost during the transfer. And usually what happens? What happened to this energy? So in reality, if you have in electrical circuits, there is always what we call electrical energy loss. So we're actually paying for that, the energy loss due to our conductors, because our conducting wires are not perfect conductors of energy. So when charges travel through these wires will actually heat up, and heat is basically just electric energy transformed into heat. So this energy that is lost can be transformed into other forms, such as heat. So you will notice that your wire will heat, or your capacitor itself will heat up. So that one. So there is always energy loss in any kind of energy transfer. So it's not always perfect that you can transmit all of the 0.058 joules of energy into the system. So there is always what we call that resistance. So energy will always be lost in reality. Okay. So that's the end of this chapter. I hope you learned something. So we will just schedule a synchronous live session so that I can accommodate all your questions for this chapter. So that's it. I will see you in our live session to entertain your questions. So thank you and goodbye.